So in our last lesson, we introduced the Gaussian integers and their corresponding norm, which will allow us to make these translations of statements that we covered in the first 2 weeks, namely Bezout's lemma, Euclid's lemma, the fundamental theorem of arithmetic. And so with the norm, we are going to be able to prove analogous results for the Gaussian integers. But first, we need to go ahead and give definitions for the things that we are accustomed to over the integers, but now write them in the setting of the Gaussian integers. So for example, what does it mean for two Gaussian integers to divide one another? What does it mean to be prime? What does it mean to be relatively prime? So these are things that we have to investigate and give some language to this. And so let's go ahead and start off with our first definition, which is that of when a Gaussian integer divides another. And so it's just going to be the same definition that we are used to for the integers. Namely, if we have two Gaussian integers, a and d, we say that d divides a if there exists some Gaussian integer k such that a is equal to k times d. And we express this as d divides a. In the same manner, the linear combination lemma from the integers continues to hold for the Gaussian integers. And for the homework, you'll go ahead and show that if d divides x and d divides y, now everything is a Gaussian integer, then d divides mx plus ny. And so the proof is going to be the same as the one that we did for the integers, just that now we're working over the Gaussian integers. And one thing that now, just so far, this seems to say that, oh, every statement is going to translate verbatim. And that's not the case. Because let's look at the following. If we take a plus bi in the Gaussian integers, we know that one divides this, but so does negative 1. And that's true for every integer. We always have the 1 and negative 1 divides these, because of course we can write a plus bi as this negative and then put a negative here. And then in doing so, we're going to get a plus bi. So we get a negative 1 does divide a plus bi. And so we have this here. But we also now have, by working over the Gaussian integers, that other things also always divide any Gaussian integer. So we can see that, so the claim is that plus or minus I divide a plus bi. And the way we want to go about showing this is, let's go through and do a plus bi over I and see what we get. Do we get back a Gaussian integer? And so this here will become a over I, and then we have plus b. But a over I, we can go ahead and rationalize that denominator. And so we multiply by I on both sides, so we're going to have a nice squared in the denominator. And in doing so, we have ai, but negative, plus b. Oops, and a typo. That was supposed to be just b. And so we have this here. So now as a consequence, we get that I times negative ai plus b is going to be a plus bi. And so we do get that I divides a plus bi. And so this is something that we have to take into account. Now we have other things that divide every single Gaussian integer. I, negative I, 1, and negative 1. And so we're going to go ahead and make a definition. We're going to call these units. And so a Gaussian integer u is said to be a unit if there exists some other Gaussian integer such that uz is equal to 1. So in other words, the units of the Gaussian integers are exactly those quantities that have a multiplicative inverse. And so this is a notion that in abstract algebra is generalized to any ring. And so in the case of the integers, the units are just plus or minus 1. In the case of the Gaussian integers, well, we're about to find out what all the units are. And we are going to see that it's just 1, negative 1, I, and negative I. But the language of units actually even extends to the integers modulo n that we have been studying. The multiplicative residues in abstract algebra are just called the units of the integers modulo n. And so that's another word for the things that we have been investigating throughout the course. And so our first result is to prove that the Gaussian integers only has 4 units, namely 1, -1, and plus or minus I. So the way that we're going to prove this is by using the definition and the multiplicativity of the norm. So proof, so let u in the Gaussian integers be a unit. So by definition, we know that there exists some z in the Gaussian integers such that u times z is equal to 1. By the multiplicativity of the norm, we have that the norm of u times the norm of z is equal to 1. But this is the beautiful part about the norm. It's always, we have as inputs the Gaussian integers, and as outputs the non-negative integers. Since n of u is non-negative, we get that the norm of u has to be exactly equal to 1. Because we're looking at all the possible factors of 1, but it's non-negative, and so we know that this could either be -1 times -1, but in this case we know that negatives are not going to happen, so it has to be +1 for both of these. So the norm of u must be 1. Now we're going to use the fact that this is a Gaussian integer. So let u equal a plus bi for a and b integers. Then norm of u is equal to, by definition of norm, a squared plus b squared, which is equal to 1. And this can only happen if a comma b are one of the following combinations. So we have 1, 0 for a, and a is 1, b is 0, -1, 0, 0, 1, and 0, -1. These are all the possibilities we can have for what a and b are. But this is equivalent to saying that u is going to be 1, -1, I, and -I. And so we are done. We have proven it. And so this is the key illustration of the norm and how we use it in proofs. We're working with the Gaussian integers, but by taking the norm, we knew that we had factorization over the non-negative integers, and since everything is here, u cannot be 0 because this is 1. Otherwise, this whole thing will be 0. So we know that these are natural. So all the things that we studied in terms of unique factorization and divisibility for z continue to hold here, and so we can exploit that property to prove, as we just did, that the norm of u is 1, if and only if u is equal to ±1 ±I. So now we can go ahead and define what it means for a Gaussian integer to be prime. So let us go ahead and take some element p in the Gaussian integers with the property that p is not a unit, and we will say that it is prime if for every a, b in the Gaussian integers such that p is equal to a times b, then this implies that a is a unit or b is a unit. And notice that this definition extends to the negative integers over z. So this definition over z reduces to saying a number is prime if p equals ab implies that a is equal to plus minus 1 or b is equal to plus minus 1, since those are the units in z. So as a consequence, we get that under this definition, negative 5 is prime in z. Since we can go ahead and write negative 5, if we write it as a times b, then we know that one of those has to be 1 or negative 1. And so in this case, we could do negative 1 for a, and b is equal to 5, or vice versa. Do it 1 and negative 5. But the key thing is that this definition does generalize the notion of prime that we are used to. When we talked about prime at the beginning of the course, we were restricted to only the natural numbers. So we never considered the case when it was negative. But now, because we are working over the Gaussian integers, and we don't have a notion for being positive or negative, we cannot do that. And so we have to allow ourselves to extend their definition. I'll also mention that in abstract algebra, when we say prime, and this is for those of you who have not taken it, the notion of prime in abstract algebra is actually the word that is used. It's not prime. That's a much stronger statement, but irreducible. And so in abstract algebra, this is the definition for what it means for an element to be irreducible. But for our purposes, we're going to be fine with this definition, since the rings that we will be studying, both notions will agree. Okay, so let's go ahead and now consider some interesting cases that happen over the Gaussian integers that go counter what we expect over z. And so with 2, what we have is that this can be written as 1 plus I times 1 minus I. And so we have that 2 is no longer prime. And so that does it for this. And then similarly, we have that 5 is not prime, because 5 can be written as 2 plus I times 2 minus I. But now notice that every time, because of the difference of squares, over here we have 4 plus 1, and over here we have 1 plus 1. And so in other words, sum of squares. And so this is the first thread of connecting the dots between what we did with sum of squares for Fermat's sum of squares theorem, and now with the Gaussian integers. And this was the thread that was first seen by Richard Dedekind in 1893, who showed that the fact that the Fermat's sum of squares theorem holds is a consequence of what the prime numbers are over the Gaussian integers. And that's where we are headed. But to do so, we need the fundamental theorem of arithmetic. And it's quite fascinating that while the fundamental theorem of arithmetic for the Gaussian integers was known, starting in the 1830s, so Gauss first proved this result, that connection that Fermat's sum of squares could be proven by just adhering to the fundamental theorem of arithmetic for the Gaussian integers would not come until 60 years later, even though it was already part of the literature. And Dedekind was actually Gauss' student. And so these are the things that we are going to be looking at in further detail. And so we now have a notion of prime, divisibility, we have units. Now let's go ahead and introduce a notion of what it means to be relatively prime. So let us go ahead and now define what it means for two Gaussian integers to be relatively prime. As with the notions we have been bringing up so far, we can't go ahead and define it as we did over the integers, because over the integers we had an ordering. So we defined it to be the greatest natural number that divided a and b. We no longer have that ordering. And so we do the next best thing. We say that two Gaussian integers a and b are relatively prime if for every single Gaussian integer d, so with the property that d divides a and d divides b, then that implies that d is a unit. And so we can let's look at 2, which is equal to 1 plus I, 1 minus I. It factors into these two Gaussian integers, and we may ask, are these relatively prime? Because if they are relatively prime, that will essentially give us two distinct prime numbers over the Gaussian integers. And what I mean by distinct is that when we think about the number 5 over the integers, 5 is prime. But now in this new definition, by extending it over to the Gaussian integers, as we just did earlier for when we thought about it for the integers, we have that now -5 is also prime, as is 3 and -3. But we want to think about 3 and -3 as being the same prime. Similarly, 5 and -5 being the same prime. And so we could ask, are these quantities relatively prime? And so this goes back to that example with 5 and -5. They are not relatively prime since their GCD would be 5. 3 and -3, they are not distinct because their GCD would be 3. And so we could ask, are 1 plus I and 1 minus I relatively prime? And it turns out that the answer is, no, they are not. And the reason is, we can go ahead and multiply 1 minus I times I. So if we do I times 1 minus I, this is going to give us I minus I squared, which is going to be -1, and so we're going to have 1 plus I. So as a consequence, what we have is 1 minus I. This divides 1 plus I, but we also have that 1 minus I divides itself. And so because we have this property here and 1 minus I is not a square, since 1 minus I is not, sorry, I said a square, since it is not a unit, we conclude that 1 plus I and 1 minus I are not relatively prime. And so we want to think about 1 plus I and 1 minus I in this new system as the analog of having 5 and -5. And so now we have these two numbers that look different upon a first glance, but they really are the same one up to unit. And this is going to be a phrase that we are going to be discussing, and we'll make this precise later, but just want to throw that out there. That 1 plus I and 1 minus I, they are not relatively prime. And the idea here is we can multiply by I to get back 1 plus I. However, if we look at 2 plus I and 2 minus I, these are the factors of the number 5. Then it is the case that these are relatively prime. So let's go ahead and show this. So we're gonna adhere to the definition. So we're gonna suppose that D divides 2 plus I and 2 minus I. So let D be a Gaussian integer such that D divides 2 plus I and D divides 2 minus I. And so now we're going to use the definition of what it means to divide. So we're going to go ahead and choose two Gaussian integers Q and T. I should say then. So then, there exists Gaussian integers Q and T such that Q times D equals 2 plus I, and T times D is equal to 2 minus I. So we have this here. Now, if we take norms, and so here's again, we're reducing it down to the natural numbers. So we take norms of both sides, so we have QD. this is going to equal the norm of Q times the norm of D, which is equal to the norm of 2 plus I. But the norm of 2 plus I is going to be 5. And similarly, we have the norm of TD is equal to the norm of T times the norm of D, which is equal to the norm of 2 minus I, which is going to be 5. But now, because the norm of D is a natural number, and the norm divides 5, we have that the norm of D is equal to 1 or 5. If it is equal to done, if it is equal to 1, we are done. So let us go ahead and suppose that it is equal to 5. So we're going to suppose that the norm of D is equal to 5. So we have the norm of D is equal to 5. But that implies that then the norm of Q and the norm of T is equal to 1. And we have, by the lemma that we just proved, the corollary 1.20, that Q and T are in the set of elements plus minus 1, plus or minus I, since they are units. So we can go ahead and divide by these. So while we have verified it explicitly, it is also worth noting that we know that Q and T divide 2 plus I and 2 minus I. So even if we did not know that they were units, we would expect that 2 plus I over Q is a Gaussian integer, since the equations tell us that it's equal to D. And so what we are going to do is do exactly that. So then we have that D is equal to 2 plus I over Q, which is also equal to 2 minus I over T. So we have this here. Now, if we go ahead and solve for 2 plus I in this equation, we have 2 plus I is equal to Q times 2 minus I over T. But we know that Q and T are units, so I'm going to go ahead and write them like this. So, in other words, we have since Q over T is itself a unit, so we have that there is a unit in the Gaussian integers such that 2 plus I is equal to U times 2 minus I. But if we go through and multiply the 4 possibilities we have by U, since U is in plus or minus 1, plus or minus I, we see that this is impossible. And that's the final part for the proof, because if we go through, there's only 4 possibilities. It can be 1 or negative 1, since that will give us minus 2 plus I. And if it was I, we'll have 2I times negative I squared, and so that will become positive 1, and similarly for negative I, and so this equality never holds. So consequently, we must have that D is a unit. And we are done with the proof. We now have that 2 plus I and 2 minus I are distinct, that they are relatively prime, and consequently they are distinct in this notion that they are not equal to a unit times themselves. And so 2 plus I and 2 minus I are really two distinct prime numbers over the Gaussian integers. Unlike 1 plus I and 1 minus I, which we showed that they were not relatively prime. So now we have these are relatively prime. So the next lemma will provide us with a way of knowing whether a given Gaussian integer is prime. So specifically, if we have a Gaussian integer z, and we know that the norm of z is prime in the integers, then z itself is also prime as a Gaussian integer. Note that the converse is not true. So converse is not true. We will show later the number 3 is a Gaussian prime, but the norm of 3 is 9, which is not prime. And so here once more we can see that relationship to the Fermat sum of squares theorem. 3 cannot be written as a sum of squares, which is equivalent to the fact that it is a Gaussian prime. And so the converse does not hold, but let's go ahead and prove the lemma as it is. So we know that norm of z is prime in the integers. So the way we're going to do this is by using the definition of what it means to be prime over the Gaussian integers. So specifically, let z is equal to a times b for some a and b in the Gaussian integers. And recall that the way that we define a Gaussian integer to be prime is that whenever we have this equation, z is equal to a times b, then a is a unit or b is a unit. So we want to show that. So we know that the norm of z is prime in the integers, and so we're going to take norms of both sides. So the norm of z is equal to the norm of a times the norm of b. Since norm of z is prime, and so now we're working over the integers. And so I'm going to go ahead and write this. This is a natural number. Since this is prime, we have that either the norm of a is equal to 1 or norm of b is equal to 1. In particular, by the corollary we showed earlier, and so this is the one we just referred to a moment back, so this is 1.20.3. So the corollary implies that a or b is a unit. So the norms are 1, so they're going to be units of the Gaussian integers. And so we have our result. We now have shown that if the norm of z is prime, then z is prime as a Gaussian integer. And so as a consequence, now we have that 1 plus I is in fact prime, as well as 2 minus I. And so the Gaussian integers 1 plus I, 2 plus I, and 2 minus I are all prime, since the norm of 2 plus I is going to be equal to 2. The norm of 2 plus I is 5. 1 plus I is 2. And the norm of 2 minus I is also 5. And so the statement that we just proved now implies that 2 plus I, 1 plus I, and 2 minus I are all Gaussian primes. And so we're done. And so for homework, you'll have the opportunity to work through the following two results. And so here we have if R and S are Gaussian integers, and R divides S, and S divides R, then R is equal to U times S for some unit in the Gaussian integers. And so this is essentially our new version of trichotomy. So we no longer have ordering over the Gaussian integers. But one of the proof methods that we use for the integers is that if A is less than or equal to D, and D is greater than or equal to A, then A is equal to D. We no longer have this. But this is the next best thing. That if we know that R divides S and S divides R, then we are guaranteed that R is equal to a unit times S. And similarly, if Q and A are Gaussian integers, such that Q is prime and Q does not divide A, then Q and A are relatively prime. And so this will be exercise 13.4.9.